Okay, this is A2Pure Maths. We are on Unit 7. This is 7.2, then the Newton-Raphson method, and this is for finding roots of equations. We want to solve an equation of the form f of x equal to 0, where x is its exact root. In this method, the first step is to find an approximate root. So the exact root is the x-coordinate of the point P where the graph crosses the x-axis. Of course it is, that's what we mean by then the root of equation, the x-coordinate, so how far along it is where this crosses. Alright, if we take a point Q very near P, and we note its x-coordinate as xr, as an approximation to the exact root, then xr is approximately equal to s. So this is our first guess. If you notice in the previous wee bit, we were kind of sure there's a root between 1 and 2, so that's a decent place to start with 1 or 2. If we know there's a root in between 1 and 2, we start with 1 or 2, and then we get closer and closer and closer using this method here. If we take a point Q very near P, notice the x-coordinate, then we have that x equal to r. So this here is like an expanded out version of the one above. So here's what we've done. We've taken this wee snapshot and made it bigger, and then put it down here, and this is this whole thing, so the Q is now kind of extended out. The coordinates of Q are xr, f of xr, as in you take the x coordinate, sub it into the function, and you get then the y coordinate, or f of xr. If a tangent is drawn to the curve at Q, which then meets the x-axis at r, and this is my next best guess, xr plus 1, 0, then xr plus 1 will be a better approximation for the root xr. From the diagram, a formula for xr plus 1 can be produced. So if we go over to the other page, then we can see this diagram again and see if we can come up then with our formula for our Newton-Raphson method. So the way we set it up then is as follows. I'm going to bring a vertical line down here from Q, and the point where it hits I'm going to call N, and we're going to base it on this right angle triangle here. So we have this, I'm going to call this angle here alpha, and I'm going to call this point here N. So what do we know? We know firstly that NQ is equal to Fx of r. So here is our point, as we bring it down. So Fx of r is the y coordinate of this point here. Alright, so hopefully we're okay with that. We also know then that tan alpha equals NQ over NR. So why is that? So NQ, because tan is the opposite over the adjacent, so NQ over NR. If you want to rearrange that, you can have then Rn, which is your distance here, equals NQ over tan alpha. Our gradient at the point Q is of course our y difference over our x difference, which is NQ over Rn, which of course as well then is tan alpha. They're just the same thing. And our gradient at Q is also equal to our point. So our f of x differentiated at the point R. So that means our third piece of information is tan alpha equals f dash xr. So if we have our 1, 2 and 3 here, and we substitute 1 and 3 into 2, we're going to get Rn equals f x of r over f dash x of r. And Rn is the difference between what we thought was our best guess and this new best guess. So our OR, which is the x coordinate of what we want, if this is our O, obviously we want this distance here. Our previous best guess was here, our ON. So from the diagram, OR equals ON, take away Rn, and that means OR equals ON, so it was our XR minus F XR all over F dash XR, and that then is effectively our Newton-Raphson method as we work it out. To get the next point, which is closer again, we get our previous point, and we take away, when we put our previous point into the function and put our previous point into the differentiated function, divide those two and take them away. That will give us then a better approximation to what we're looking for. Next video then we'll take a wee look at a couple of examples.